constant acceleration. Learning objectives. After reading this module, you should be able to 2.13 for constant acceleration, apply the relationship between position, displacement, velocity, acceleration, and elapsed time. 2.14 calculate a particle's change in velocity by integrating its acceleration function with respect to time. 2.15 calculate a particle's change in position by integrating its velocity function with respect to time. Key ideas. The following, the following 5 equations describe the motion of a particle with constant acceleration. Number 1, velocity equals initial velocity plus acceleration times time. Number 2, um, velocity equals velocity squared equals initial velocity squared plus 2 times acceleration x minus initial x. Number 3, x minus x initial x equals initial velocity times time plus half acceleration times time squared. Number 4, x minus xo equals half initial velocity plus velocity times time. Number 6, x minus xo initial x equals velocity times time minus half acceleration times time squared. These are not valid when the acceleration is not constant. Constant acceleration, a special case. In many types of motion, the acceleration is either constant or approximately so. For example, you might accelerate a car at an approximately constant rate when a traffic light turns from red to green. Then graphs of your position, velocity, and acceleration would resemble those in figure 2 to 9. Later, when you brake the car to a stop, the acceleration or the deceleration in common language might also be approximately constant. Such cases are so common that a special set of equations has been derived. For dealing with them, one approach to the derivation of this equation is given in this section. A second approach is given in the next section. Try out both sections, and later when you work on the homework problems, keep in mind that these equations are valid only for constant acceleration. First basic equation. When the acceleration is constant, the average acceleration and instantaneous acceleration are equal, and we can write action 2-7 with some change in notation as acceleration equals acceleration average equals v minus initial velocity minus initial velocity divided by time minus 0. Here, initial velocity is the velocity at time equals 0, and velocity is the velocity at any later time. We can recast this equation as velocity equals initial velocity plus acceleration times time. As a check, note that this equation reduces to velocity equals initial velocity for time equals 0, as it must. As a further check, take the derivative of equation 211. Doing so yields the phi equals acceleration, which is the definition of acceleration. Figure 29b shows a plot of equation 211. The velocity time function, the function is linear, and thus the plot is a straight line. Second basic equation is in a similar manner. We can rewrite the equation 2 with a few changes in notation as velocity average equals x minus initial x divided by times minus 0, and then as x equals initial x plus velocity average times time, in which initial x is the position of the particle at times equals 0, and velocity average is the average velocity between time equals 0 and a later time. For the linear velocity function in equals 211, the average velocity over any time interval, say from times equals 0 to another time, is the average of the velocity at the beginning of the interval equals initial velocity, and the velocity at the end of the interval equals velocity for the interval from time equals 0 to the latter time times time, then the average velocity is velocity average equals half times beginning of velocity plus end of the interval velocity. Substituting the right side of equation 211 for v yields after a little rearrangement, velocity average equals initial velocity plus a half times acceleration times time. Finally, substituting the equals 214 into equation 212 yields x minus initial x equals initial velocity times. Finally, substituting equals to 14 into equals to 12 yields x minus initial x equals initial velocity times time plus half times acceleration times time squared. As a check, note that putting t equals 0 yields x minus x initial x as it must. As a further check, taking the derivative of equals 215 yields equals 211 again as it must. Figure 29a shows a plot of equals 215. The function is a quadratic and thus the plot is curved. Three other equations, equation 211 and 215 are the basic equation for constant acceleration. They can be used to solve any constant acceleration problem in this book. However, we can derive other equations that might prove useful in certain specific situations. First, note that as many as 5 quantities can possibly be involved in any problem about constant acceleration, namely x minus initial x, acceleration, time, acceleration, and initial velocity. Usually one of these quantities is not involved in the problem, either as a given or as an unknown. We are then presented with 3 of the remaining quantities and asked to find the fourth. Equation 211 and 215 each contain 4 of these quantities, but not the same 4. In equation 211, the missing ingredient is the displacement x minus initial x. In equation 215, it is the velocity. These two equations can also be combined in 3 ways to yield 3 additional equations, each of which involve a different missing variable. First, we can eliminate time to obtain v squared equals initial v squared plus 2 times acceleration times x minus initial x. This equation is useful if we do not know time and are not required to find it. Second, we can eliminate the acceleration between equals 211 and 215 to produce an equation with which acceleration does not appear. X minus initial x equals half initial velocity plus velocity times time. Finally, we can eliminate the initial velocity, obtaining x minus initial x equals velocity times time minus half acceleration times time squared. Note the subtle difference between this equation and equals 215. One of involves the initial velocity, the other involves the velocity at time. Table 2.1 lists the basic constant acceleration equation equals 211 and 215 as well as the specialized equation that we have derived. To solve a simple constant acceleration problem, you can usually use an equation from this list if you have the list with you. Choose an equation for which the only unknown variable is the variable requested in the problem. A simpler plan is to remember only equation 211 and 215 and then solve them as a simultaneous equation whenever needed. Thank you. That's all from me.